Well, we're very pleased to welcome yet again Scott, who's always welcome, and he's going to tell us what he's going to talk about.
Okay, so I have, I'm going to turn my screen share on in a moment. I have in my hand a plastic model of a cross cap. And this is after reading George Francis's book and doing some work with modeling. So as you can see, there is a boundary here, which is unknotted, and there's another boundary on the inside where my fingers are showing, which is also unknotted. So if you close this off, you get a broken surface diagram of the cross cap. And I'm going to show you more of that in drawings in a little while. Meanwhile, working on sharing the screen. And whoop, okay, right. Wait, that's the wrong one. Okay, there we go. Here we go. This is today, I think it's February 1st, and we're going to talk about braidings. This is from a chapter in diagrammatic algebra, which is written by these two people here. And this is a photo of their younger selves. I looked on the whiteboard over here and I read that braid word, which is 1 bar, 3, 2, 2, 3, 2, 3 bar, 1 bar. And it turns out it's a 3 colorable knot. So we can construct an immersion. Sometimes it's an embedding. I think that's going to be an embedding in this case of the threefold branch cover of S3 branched over the knot or link. This is either going to be 7-4 or 6-1, I think. And so this is going to be braided, in 5 space. It's going to be rather explicit by the time the day is done. Before I'm not going to actually do that with this example, but I should show you the outline of how to do this with this example. Before I do that, I want to correct some notational errors that I had last time. I talked about a 2 arrow that went from the source 1 arrow A to the source 1 arrow to the target 1 arrow B. That 2 arrow would be named F, and that would replace a commutative diagram. And what I should have done is rotated this diagram around this axis, reflected it in the plane to get the diagram below, which then I can glue along either A or glue along B, and then compare the result to either the identity 2 arrow on B or the identity 2 arrow on A. And I had neglected to turn this diagram here upside down in my previous talk. So let's get back to the cross cap. This is actually a non-example of what I want to talk about, but it's a good non-example to start with. So this is an embedding of RP2 and R4. This is a movie description of it. So at the bottom of the movie, we have a birth. Then I have a cusp. and this looks like it's a right cusp down. And then there's a Rademeister type 1 move, and that Rademeister type 1 move gives you this little Harry Potter thing here. And then there's a side bounce over here, and then a saddle, and then the saddle is over here. And then the maximum that I'm indicating here moves to the left, and that leaves the crossing here. And then there's another cusp. There are a pair of cusps, and there's a type 1 move, and then a death. And if you compute the writhe of this diagram, you'll see the writhe is -1. If you compute the writhe of this diagram, you'll see the writhe that's +1. And so the change in writhe from here to here goes from 0 to -1. So the change in writhe is negative. The change in writhe here is negative. And so the normal Euler class of this embedding is -2. So the twofold simple branch cover of S4 that's branched along RP2, where we have a -2 normal Euler class, is CP2. And I haven't worked out all of this bit here, but the involution on -CP2 that gives S4 is induced by complex conjugation. I guess that's a homework problem. And I just want to remind you that CP2 is made from 3 different cells. There's a 0 cell, which is just a vertex. There's a 2 cell, which wraps around and touches the vertex. And then there's a 4 ball that's attached to the sphere here, and the attaching map is given by the Haupt vibration. So if you start with CP2 and you look at this sphere, apply complex conjugation, then it will quotient out to a cross cap, and that gives you the twofold branch cover. Now, as far as I know, CP2 can't be braided or immerse braided in 6 space. And if there's a characteristic class reason for that, later on we'll see a few braidings of other branch covers of S4 that are branched along surfaces, but it can't be done for CP2. And why it can't be done is a bit of a puzzle. I'd like to be able to use these diagrams to try to get the characteristic classes. I'd like to be able to visualize them by means of this. And later on, what I'm going to do is actually, for any one of these.
Sorry,
yeah,
an idiot. But what do you mean by braiding?
I'm going to tell you in a moment.
Oh, okay.
Yep. No, you're not being an idiot. I'm just getting ahead of myself. So not at all. The point, though, is that I don't know what to do here, and I don't know what to do here. And I asked Perugolini about this, and he told me something that I didn't understand. So the next time I see him, I'm going to have to ask him again and see if I can get him to explain this. So I like this model of the cross cap, and you actually can make it. So if you take a strip of paper and you cut quarter of the way down the strip of paper, and mark on the front and the back where you would ordinarily construct a Mobius band. So you mark this segment A, mark this segment B, fold them over as indicated, and then when you fold them over on the front, you might see this, on the back, you might see that, and then do a quarter of a twist as indicated on each of these pieces. Do the same thing in the back, and you'll get a broken surface paper diagram of a Mobius band, where the boundary, there are 2 boundaries, just as I had in the plastic model. So one boundary is patently unknotted, and the other one is also unknotted. And this is, I learned this from George Francis. As it happened, somebody on Twitter had tweeted a picture of Z goes to Z squared. And so I copied that picture off of their site, but as on Twitter, I didn't know whose name it was, so I didn't credit them. There's a feature in this area here that I'll call your attention to, but the Z goes to Z squared is the prototypical example of a two-fold branch cover. And so if you take x plus iy and you take the graph of Z goes to Z squares, you're going to have two components, x, y, and then you'll have these other two components here. If you look at that on the two disk, you get something that looks like this. You project it into three space. You can just take an orthogonal projection, you'll get something like this. And if you rotate it around, you'll see this branch point. You'll see this saddle going on here. So again, from George's book, this is, according to George, this was at some time more than 40 years ago, a Joan Berman's favorite involution. So you take the torus, you skewer it and put a 180-degree rotation upon it. And then one side of that torus is going to be this, and then things are glued together. And the way they're glued together is we'll indicate that quotient by means of a diagram like this. But let's back up just a bit. And I promise you, Roger, I will get to what I mean by braided, and I know that there's a slide that says that. So if we have two concentric spheres, both of which have an outward pointing normal, and we want to attach a handle between them, then you can't just attach a tube without messing with the orientation. So what you have to do with a tube is you have to twist the tube with a 180-degree rotation and attach one side to one face and another side to the other face. And that 180-degree rotation is going to have those two branch points over here. So this is a broken surface representative of that. Again, this is a computer drawing of Z goes to Z squared. We're going to think about the bottom as being a braid generator sigma I, and then the top is the identity, and that it is sigma I just means that there are I sheets on one side of it. And once we fixed a braid index, we know how many sheets are on the other side of it. So the I on it is a substitute mark. There's this thing that I call a chevron or a Star Trek chevron perturbation of this, which in movie form goes like this. We start with a crossing, we add a cusp, we add another cusp, we move the maximum point past the crossing, then we attach, in this case, it's a fork. We do a psi move, do a type 1 move to get to here, and then straighten things out. And the diagram of that process is this Star Trek chevron, which is a generic perturbation of this picture here. And so this picture is what we'll call a black vertex. So when you see red, it's black. How about them dogs? Okay, so this picture here is the pair of concentric spheres with a handle attached, and the red arc indicates the branching, or indicates the time elapsed braid generator. This is a more detailed drawing thereof. So in a movie, you have a birth, you have a birth, you have this black vertex, you have this broken surface diagram, and then you have a black vertex here. So this is the twofold branch cover of S2 with two simple branch points, and we'll denote it by means of a red arc with two black vertices here. And this is one of the examples of Kamada. This is a Kamada chart in the disk. And tacitly, whenever I draw a picture in the plane or in a disk, we think about that disk, we plug it into the two sphere like that. And we'll come back to that. So when we go back to the torus, we can read this diagram as a movie. We can read it as identity, sigma 1, identity, sigma 1, identity. So these correspond to cross sections here, 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 and here. And at any time in the process, we take a break closure, and then at the top and the bottom, we just cap those off with, first we cap off the inner circle with a disk, then we cap off the outer circle with a disk. And so those disks are here on the sphere. Okay, so I am going to tell you what braiding is, but I want to just go through a short excursion one dimension higher. So if we start out with concentric spheres, the chart for that would be this. Now in this chart, there's a tacit braid index. So there's a braid index 2 here. And this thing would be labeled with a 1. And the process of going from these two concentric spheres to this is the attachment of a 1 handle. And we can actually go a bit more. So if we go empty chart, say with braid index 2, braid index 2, braid index 2, braid index 1 here, then this movie process, empty, arc, empty, can be replaced with a disk, and the corresponding braided surfaces, surface braids, are going to be two concentric spheres, the twofold branch cover of the sphere with two branch points, two simple branch points, and then two concentric spheres. And so here's a movie of this curtain, and the movie of the curtain describes this movie. And once again, you have these two concentric spheres, each bounds a ball, then a 1 handle is attached, and then a 2 handle is attached, and then each of these spheres bounds a ball. And so this is the twofold branch cover of S3, branched along an unknot in S3. And this glyph describes the braiding thereof. We'll go one more step, and we can get the twofold branch cover of S1 cross S2 braided in S2 cross D2. And so why am I calling these braidings? Well, a classical braid, if you think about it, it lives inside S1 cross D2. And if you project the braid onto the core circle, then that's actually a covering space. So this braid lives inside D2, S1 cross D2. You project down to the core circle here, and that's a covering map. So what we're going to do is, now I think we finally get to the definition. So we're going to say that a simple branch, by simple I mean that the branch points have neighborhoods that are z goes to z squared, and in the other direction it's a product. So a simple branch cover is braided if we can embed or immerse it in SN cross D2 such that when you project down to SN, that composition induces the covering map. Okay, now I've finally answered Roger's questions, so let me ask, are there any questions about that idea?
I have a question.
Yeah,
your earlier example of a cross cap or Mobius strip. Why does it have two boundary components?
So one boundary component you just cap off inside 3 space. The other boundary component is a disk that pushes into 4 space. So it's actually supposed to be, it's a broken surface diagram of the cross cap embedding of RP2. Do you want me to pull that picture up so we can talk about it again?
Well, I seem to remember the Mobius band only has one boundary component.
Right. But so let's see, where is this thing? It must be in here somewhere.
It was in your hand, the plastic thing.
Yeah. Okay. Right. But if I want to construct
a band with a hole in it,
I have a Mobius band with a hole in it. Now, if I cap this off, and I actually have a model where it is capped off, then there's only one boundary component. So this, let me go ahead and pick that up. Here we go. This one only has one boundary component, so it is a Mobius band.
Scott, I think you're not showing.
Well,
you're just showing one of your category pictures.
Oh yeah, I understand that, but in a different screen, I'm showing it, but maybe that's not what's focusing. So let's do it there. Okay, so okay. Here we go. There it is, and it's only got one boundary component. So I can't, in this case, I capped off the other boundary component. So this is actually an embedding of a Mobius band with 2 branch points.
In R4.
If you put that disk into R4, it embeds as a cross cap. Okay, so let me get back to where we were. We were talking about braiding, which was about here. Okay. All right. Did I answer your question, Dale?
Yes, thank you.
Okay, so that's that thing is not braided, but the neighborhoods of the branch points are similar to what we had before. Right. So we want to develop some glyphs that describe pieces of braided surfaces. One of those glyphs is going to be either a cup or a cap, and there's an orientation. And there's an index on the glyph, which is an I, which is a braid index. So if you think about this X as lying, being a sigma I, then this would be X bar. And so the glyph describes the process that goes from, that goes from the identity braid to the braid sigma I bar. And similarly, these other glyphs either go in the other direction or the bar is in a different place. And that is that's a Reidemeister type 2 move, as I think you know. To relate this glyph to what we did last time, we're going to take our T and F both to being 2 points. P and B is either going to be a negative crossing or a positive crossing. And so when you go from 2 points to 2 points, you go, say, by means of a negative crossing, then you go by means of a positive crossing, and then you can take that composition and compare it to the identity on 2 points, which would be straight strings. We'll require conditions of those glyphs. These won't come in immediately, but we'll require that a circle can be annihilated, and then these can be saddled. And you do need an orientation convention on that. So, for example, this is one possible orientation for which that holds. Okay, and also we'll require zigzag identities for those glyphs. The next glyphs come from the Reidemeister type 3 move. So the Reidemeister type 3 move describes in 4 space, it describes this broken surface diagram. So the broken surface diagram, you'll have a top sheet, a middle sheet, and a bottom sheet. The bottom sheet in the broken surface diagram is broken into 4 pieces. The middle sheet is broken into 2 pieces, and the top sheet remains unbroken. So from this schema, we abstract this glyph here. The serifs on the glyphs are crossings, and the vertex is called a white vertex. And the bookmarks are just braid indices. So you're going from sigma I plus 1, sigma I, to sigma I plus 1, sigma I. And this is what Kamada calls a white vertex. We won't be adorning things with these serifs on them. We have crossings, which correspond to the distant braid generators. So as long as I plus 1 is bigger than J, then you get these crossings. There, of course, you also have other orientations involved here. And as I said, this is what we mean by a black vertex. So the totality of our glyphs are black vertices, crossings, white vertices, and maxima and minima. And this is a lovely example due to Seiichi Kamada. So this example describes the, this is a braid chart for the 2-twist spun trefoil. And I'm sorry, it's for the spun trefoil, excuse me, it's for the spun trefoil. And it represents a surface braid that has 1, 2, 3, 4 4 branch points. Oh, I see what I did. Okay. It has 4 branch points, as I indicated. There are 4 simple branch points. It has braid index 3 because the indices on these arcs are 1 and 2. So it involves three string braids, and the if you read from the bottom to the top, you'll see 2 bar 2, 2 bar 2 bar 2 2, 2 bar 2 bar 2 bar 2 2, 2 bar 2 bar 2 bar 1 2 2 2, etc. And so if you read from bottom to top by means of those cross sections, you'll get this sequence of braid words. And this is a corresponding movie of that braided surface. And at these particular points, those are where the black vertices are occurring. We could, but I won't, we could actually color these different arcs to see that it indeed is knotted. This is another marvelous example of Kamada's. This is the braid chart for the 2-twist spun trefoil. So this is the braid chart of the 2-twist spun trefoil. It involves 4 strings, 4 sheets, and there are 1, 2, 3, 4, 5, 6 simple branch points. And the colors here are meant to re-emphasize that this is 3, this is sheet 2, this is sheet 1. So if we took a cross section over here and we read right around here, we would see 1, 2, 1. If we took the cross section on the other side, we would get 2, 1, 2. So the white vertices correspond to the braid relation, the Yang-Baxter relation. These crossings correspond to the fact that 1 and 3 commute, and the black vertices correspond to what we drew before. I want to introduce solipses. So these are nodes, and these solipses either come in the form sources or sink. So the glyph for the solipsis is this vertex here, and this corresponds to a crossing change at the surface. So we go from the braid generator sigma I to sigma I inverse, or vice versa. And the relations that the solipses are going to satisfy is we can either introduce a source sink pair of solipses. Question? Okay. And we can also push a solipsis off of a black vertex. And so we can just push that here. So these also come in cup form, and this can come either as a lambda or as a Y in a Y form. Later on, it's going to be worthwhile to keep track of the orientations of sheets. And so the orientations of sheets are just kept track of by means of a color. And I don't want to labor on that idea just yet. So let me just remind you that we want to construct branch covers of knots, construct branch covers of S3, braidings of branch covers of S3, branched along knots. There are so many adjectives in there that phrase is a little bit annoying, but in order to do that, we need to allow our charts to move. And one way that the chart can move is that this black vertex can bend around. I've changed horizontal and vertical with left and right. Another thing that can happen is that the black vertices can move past each other. There are a zillion versions of this. I don't think that these pictures are exhaustive here. But I get tired when I write all possible versions of these. So we can bend black vertices around and we can move black vertices past each other. And now, this is something that many of you have known since your childhood, namely that if you take a thrice twisted, put 3 half twists in a piece of paper and glue it together, you get a Mobius band. And if you cut it down the middle, you'll get an annulus. So we're going to construct the branched cover, simple branch cover, two-fold branch cover of S3 branched along the trefoil. And the way we're going to do that is we're going to just construct it by means of a movie. So to go from the empty picture to this arc means that we've started out with a pair of concentric spheres, each of which bounds a ball. Then we attached a one handle between them. Here we'll attach another one handle between them. At the next level, we'll introduce a pair of solipses. And then we'll move these black vertices past, we'll move the solipses past these 2 black vertices to get to this picture. Then we perform what is a Roseman move, so that's an isotopy. And then these other things are isotopies. And then on the right-hand side, we're going to start twisting. So we bend this black vertex here, move it past the solipsis, move it past the other black vertex, move the solipsis past the maximum, move this past the solipsis, and then straighten out the string. Do that whole process 3 times, and that's what's going on here. And then when you get back here, bend this back, do a Roseman move, get rid of these solipses, shrink this arc, shrink the other arc. And so that whole process describes a non-orientable Seifert surface for the trefoil that you cut 2 copies of S3 on, and then you braid them using this sequence of charts.
Well,
Yeah.
Does the solipsis represent a sort of self-intersection of the surface or something?
Yes. Yeah. In the cross section, you have 2 double points. So in the entire process, in this particular braiding of the two-fold branch cover, which is, I guess, a lens space. We're going to see that it's a lens space. There is actually a loop of double points there, which is the trace of the path of the solipsis in the process. Right, we're going to see that this is in fact a lens space, because from here above you have, let's see, 2 concentric spheres, 2 one handles between them. Remember, this is a torus, so this must be a solid torus here. Similarly, this is a solid torus here. These are obtained by attaching one handles. These are obtained by attaching 2 handles. And this whole process here, that's 3 twists. And so this is a 3-1 lens space. And it's quite nice in that in order to perform the Dane twist, you don't actually have to cut things up. You don't have to cut the thing up and twist around. So there you go. Did I answer your question, Roger? It looks like you're saying something, but not.
Sorry. Yes.
Okay.
Did I?
Okay, good. Okay, so I need to breathe. which means I need to look at what time it is. Okay, good. Wow, we have a lot of time. Sorry, I'm talking too fast. So we're going to promote things one more dimension. And so there are moves for braid charts. Here are some of them. Many of them are quite obvious. If you have a crossing followed by a crossing, you can undo it. If you have crossings where strings are far enough apart, you can do a Reidemeister type 3 move. You can also move across a sequence of crossings through a white vertex. And you can push a crossing, black vertex through a crossing, get rid of it. These are all expressions of certain naturality conditions. Exchange followed by exchange is exchange followed by change. You have psi moves for crossings and optima. And you have everybody's favorite, the Zolochnikov equation, the quadruple point move, which strangely enough, in the examples that I played with, I haven't had to use this yet. And so it's kind of surprising. What we'll do in a bit is we'll actually pull black vertices through white vertices in one of these fashions as indicated. Two white vertices cancel. And let's get back to something that I'm hoping that we all understand, which is that we have the 3 coloring of the trefoil. So the 3 coloring of the trefoil will have indices 1, 2, and 3 upon the trefoil, so that if we have 2 colors coming into a crossing, then the other under arc has the 3rd color. And so this is actually a permutation representation of the fundamental group. So this is not the best notation, but we'll let 1 correspond to the transposition 1, 2, 2 correspond to the transposition 2, 3, and 3 correspond to the transition 1, 3. And now with this 3 coloring, I'm going to use the 3 coloring and I'm going to construct a braiding of the 3-fold branch cover of S3 branched along the trefoil. And the braiding I'm going to describe is in terms of a movie of Kamada charts. So each still in the movie is a braid chart, and this is how it goes. We start out with 3 concentric spheres. We attach a 1 handle between the first and second sphere. Then we attach a 1 handle between the second and third sphere. So at this point, we have a braided 2 sphere inside 4 space. And then we're going to start moving this black vertex past the other black vertex. So we're going to move it in front. Now, I thought that this was just a typo, but in fact, what I want to emphasize at this stage is that if I go from this base point and I cross 1, go around 2, and I come back again, then the sequence of words that I'll get is going to be, well, if I just read them without orientation, it would be 1, 2, 1. And so that's where the purple sheet comes in, because everything is measured with respect to a base point over here. Okay, so now let's go ahead and start doing the twisting. So we twist, we bend these back, we again move this in front of that. bend them back again, move them in front. We get to this picture here. And so we've done this whole bit describes the twisting in the trefoil, but we're in a bit of a thrackle here, to quote John Conway. So we're going to have to undo that process. So I'm going to just flatten that out a bit. What's important is that the relative positions of these black vertices has to stay in place. So the first thing that we're going to do is we're going to push this black vertex through these other two sheets. And I forgot to mention that in order to do this move, I need these two arcs to be oriented coherently. When I push the black vertex through, it becomes a white vertex is created. The orientations are respected, and we get this picture here. Then the next thing I want to do is, well, this red arc is oriented to the right. This red arc is oriented to the left. And so I can do a Roseman move, a Roseman saddle move, type 2 saddle move right here. And then I can straighten out that arc. And as long as I don't do anything violent, I can just leave that way off to the right. The next thing I want to do is I want to take this arc is oriented upward. This arc is oriented upward. So I can take this black vertex, push it through the white vertex and get rid of the white vertex, leaving me with a loop here, and this bent blue arc. And let the loop die, let this loop die, and bend this back, let the red arc die, let the blue arc die, and as Roger would say, Bob's your uncle. And so we've described the braiding of the the braiding of the threefold branch cover of S3 branched along the trefoil. One thing that I haven't done with this yet is, oh, right, I guess I should explicate this just a bit. So if we have a cross section like this, I'm going to turn it on its side so that it's easier to read. We can write that as a braid movie. I think I wrote the movie in the wrong order. So we have the empty word 1, 2 bar 2, etc. And so we just read along the non-critical levels and we get a sequence of braid words. And so, for example, this braid word here corresponds to this diagram here. And one of the goals that I have in mind for this is I'd like to be able to understand Perkos linking forms in terms of these braidings of threefold branch covers. I think it's doable. I just haven't been able to master it yet. So let me extend Seiichi's braid chart. Remember that we had this braid chart before, which consisted of 3 concentric circles in 2 arcs. And these circles were labeled 2, 2, 2, and these arcs were labeled 1 and 1. Then if we sort of cap that off from both ends, then we get this braid chart here, and this is actually a braiding of a knotting of S3 and S5. So here we have a knotted S3 and S5 that's described by means of this. You can check that it's knotted because you can actually 3-color the thing. And it's the spin of the trefoil, I think. Okay, so let's move up one more dimension, if you haven't had enough. So we can look at the twofold branch cover of S4 branched along the 2-sphere, an unknotted 2-sphere. Well, that's still S4. That's analogous to our previous pictures, which consisted of a disk or simply an arc, as long as you put some outward pointing orientation on that thing. If we take the twofold branch cover of S4 branched along a torus, we would get S2 cross S2. And we can actually fill the torus in as a solid torus and get a sequence of charts, which would consist of a red disk like this, then a pair of red disks, and then a red disk, and the death. The last example I want to talk about is the Klein bottle. And before I do it, I want to give you a movie of the surface. This isn't your ordinary standard Cliff Klein bottle. This is the one that has 2 branch points in it. So the movie goes like this. You start from nothing, have a birth, you perform a fork, and you get 2 curves, then twist one of the curves by means of a Reidemeister type 1 move, and then untwist it, and then add a saddle here, and then let that die. So that's the movie of the Klein bottle. And let's fill these things in with appropriate discs. So here we have a disc. Then there's a critical point that occurs here. This disc, as I said, I'm going to have to use color. And so this disc starts twisting, and when it twists back here, the color isn't indicating a braid index in here, it's just indicating front and back. Then we introduce an arc of solipses here, and then let the solipses push off to the other side. So there's a whole disc worth of solipses that's occurring, but that allows me to change the orientation back and push that back. So every single chart here represents a twofold branch cover of S3 branched along either a single knot or an unknot. And then there represents a braiding thereof. And so the entire process represents a braiding of the twofold branch cover of the Klein bottle. And so, for example, if you look at this, you can rewrite it as a chart movie where the space between here is just empty. And this is what the chart movie looks in terms of solipses. And there is a thanks here, so I think I'm done.
Thanks very much, Scott. Are there any questions? Do you remember I wrote to you about a week ago about a paper I wrote with Dale?
Yes.
Did you manage to, can you interpret those immersions as in your language?
Yes, the verb is can, and I can do it. Have I done it? No, I haven't, because just requires more drawing time than I have at the moment. I plan to do so because I'd like to get back to better understanding link homotopy from these points of view. So the question from Roger has to do with when was it? Sort of late 80s, link homotopy was quite the fashion. And Paul Kirk's dissertation defined an invariant for link homotopy spheres. And then Kent Orr showed that Kirk's invariant was trivial, I think. But link homotopy spheres are very, very interesting, and they deserve more attention than they've gotten in recent history.
So, I mean, maybe we can have a chat about it sometime.
Yeah, I want to draw those pictures. So there are too many of me here. So let me get rid of one of them. There we go.
Remember that paper, Dale? We wrote
Yeah.
Sussex.
Sorry, my office is over the garage and my wife is driving out. So she's just closed the garage door. That's what all the rumbling is. It's not an upset stomach. Any other questions?
Here's the sort of question. There's a construction we've used for a long time, which we call something like cyclic suspension or cyclic branch covers, where every time you have a codimension 2 branch covering in a certain situation, you get an embedding of that in the next sphere, and then you can do another one, and you can make towers of them. It would be interesting to see how that fits into your schema.
Yeah. So I think that concentric sphere, 3 concentric spheres with the 2 disks, might be a phenomenon of that sort.
Mm-hmm.
But
Sorry, Lou, I wasn't concentrating. Can you repeat your question?
Breeskorn manifolds, for example, can be viewed as being obtained by iterated branched coverings. You could start with a trefoil knot. You could take the 5-fold branch covering of that is a 3 manifold, but it's naturally embedded in a 5 sphere, and then you do it again, and you can see that this kind of construction can be iterated. So there are iterated branch covering constructions that make lots of interesting high-dimensional manifolds. So I was wondering how these kind of iterated branch covering constructions fit in with Scott's schema.
So one of the things that we can do, but we haven't done, is these are all simple branch covers. And so if you have non-simple branch covers, there's a calculus of that, which is somewhere between Seiichi's brain and my brain, and probably Ricardo's brain as well, among those 3 locations. We should be able to develop that calculus to give, for example, a chart movie of the 5-fold branch cover. We just haven't done it. It gets very gnarly very quickly. But yeah, that's a worthwhile endeavor.
Any more questions? Well, many thanks, Scott.
Happy New Year, everybody.
Yep, happy.
Thank you.
Which particular New Year?
I think it's the year of the tiger.
Tiger, yeah.
Right. Okay. That's Asian tiger man. Yeah. So, we'll see you all next week, I hope.
Who's talking next week?
Well, that's a good question. Scott, did you want to talk again, or are you fed up?
I think the question is whether you're fed up with me. I have a very elementary talk about what's it called? Binary octahedral group that I can give. But it's a bit elementary.
You like elementary?
It would tie in, I think, with your geometric groups talk.
I could give another talk on geometric algebras.
Yeah.
Maybe.
Why don't you have a break from me, and then I'll come back with that. Volodya should be giving a talk, I think.
Who?
Vladimir.
Oh, Vladimir. Yes, of course. Yeah. Yeah. There's a half term break coming up soon because I'm going away somewhere. I don't know where, but I'm going away. It might be Georgia, and I don't mean southern state. Whatever. Anyway, so thanks again, Scott. I'll send around details when we sort it out. Bye now.
Bye.
Okay.
Aye.